Every measurement you've ever trusted, every ruler, every clock, operates on an assumption so fundamental we rarely question it, that the very fabric of matter, the bedrock of our existence, remains constant. For a century, cosmology has painted a picture of an expanding cosmos, its galaxies racing away, its horizons stretching into infinity. But what if this grand narrative, so fundamental to our understanding of reality, is a profound deception? We gaze at distant light, red-shifted, convinced it signals space itself ballooning outward. Yet, a radical hypothesis emerges from the fringes of cosmology. The cosmos isn't growing, we are shrinking. This isn't just a tweak to our equations, this is a complete inversion of reality, implying an existential horror where our perception of scale, our very being, is eroding, unnoticed, with every passing moment. Imagine a reality where the mass of every elementary particle, the very quanta of existence, has been imperceptibly increasing since the dawn of time. A relentless, silent shift that would diminish every atom, every cell, every star, every measuring tape, and every human observer, making the distant universe appear to recede when, in fact, it is our local scale that is perpetually contracting. Tonight, we will dismantle our comfortable cosmic assumptions. We will explore the chilling hypothesis that challenges the very notion of an expanding universe, delving into the physics of a silently shrinking reality, the paradoxes it creates for observation, and the profound, unsettling implications for our place in an ever-diminishing cosmos. If you're ready to confront a reality where the universe might be shrinking beneath your feet, hit that like button and subscribe to Terran. Prepare yourselves. We begin. For nearly a century, our understanding of the cosmos has been anchored to a singular dramatic truth. The universe is expanding. From the faint afterglow of the Big Bang to the accelerating recession of distant galaxies, every major observation seems to confirm this colossal stretching of space-time. The telltale signature is redshift, the phenomenon where light from faraway celestial bodies appears stretched, shifted towards the red end of the spectrum, much like the pitch of a siren dropping as it moves away. This cosmic reddening is universally accepted as direct evidence that space itself is physically expanding, carrying galaxies along for the ride. But what if this bedrock principle, this cosmic narrative we've meticulously constructed, is fundamentally misread? What if the universe isn't getting larger, but rather, our very perception of scale, our fundamental units of measurement, are subtly, relentlessly diminishing? This is the unsettling core of the shrinking universe hypothesis. The expansion we observe is an illusion, a cosmic mirage caused by the imperceptible increase in the mass of every elementary particle throughout time. Consider the photon, the quantum of light that delivers information across unimaginable distances. When an atom in a distant galaxy emits a photon, its unique spectral fingerprint, its specific wavelength, is determined by the energy transitions of its electrons. These energy levels, in turn, are precisely calibrated by the fundamental constants of physics, including the mass of the electron. If, as this radical hypothesis suggests, the mass of elementary particles has been steadily increasing since the early universe, then atoms in the distant past would have possessed slightly less massive electrons. A photon emitted by such a lighter atom in a nascent galaxy would therefore have a subtly lower energy signature, corresponding to a longer wavelength than a photon emitted by an identical but heavier atom here on Earth today. As this ancient photon journeys across billions of light years, it retains its original lower energy. When it finally strikes our telescopes, our detectors, and ultimately our eyes, it interacts with matter built from these now more massive particles. We compare the incoming photon's energy to what our local, heavier atoms would produce. The discrepancy isn't because space expanded, it's because the fundamental energy scale of our local reality has subtly but profoundly shifted. The photon, born in a universe of lighter particles, appears redshifted when measured against our present heavier atomic rulers. This reinterpretation transforms redshift from a cosmic expansion indicator into a cosmic age indicator. The degree of redshift then becomes a direct measure of how much the elementary particle masses have increased since the light left its source. A greater redshift would imply light coming from a more distant, and thus earlier, epoch when particles were even less massive. This subtle, cumulative change over vast cosmic timescales would precisely mimic the effects of an expanding universe, creating a grand illusion that has shaped all our cosmological models. The implications are immediate and deeply unsettling. Every meter stick, every atom in our bodies, every oscillation of a cesium clock is ultimately defined by the properties of these elementary particles. If their masses are increasing, then everything composed of them is effectively shrinking relative to a fixed external scale, a scale that, by definition, we cannot access from within our diminishing reality. Our rulers are shrinking, our clocks are subtly speeding up, as oscillation frequencies depend on particle masses, and our very bodies are growing denser, smaller, all without our conscious awareness. We become prisoners of a relative perception, constantly calibrating our shrinking world against itself. This perspective challenges the very notion of fixed units in the universe. We assume that a kilogram, a meter, a second are immutable standards, but if the fundamental constants that define these units are evolving, then our scientific framework, built on these supposed bedrock assumptions, might be resting on a shifting foundation. The universe, in this model, isn't dynamically stretching space. It's subtly altering the intrinsic properties of matter itself, resulting in a world where everything appears larger at a distance simply because our present-day scale is smaller. The elegant simplicity of this idea, that the universe's grandest illusion stems from the most microscopic of changes, carries with it an almost philosophical horror. Every moment, every breath, every heartbeat, we are shrinking. Not in a catastrophic, noticeable way, but with an insidious, relentless creep that redefines our relationship with cosmic scale. The galaxies aren't running away from us, we are shrinking away from them, making them appear ever more distant, ever more redshifted. The cosmic void isn't growing, we are becoming smaller within its apparent emptiness, our perception of its vastness amplified by our own diminishing stature. This hypothesis forces a radical re-evaluation of fundamental physics. It suggests a universe not driven by the stretching of a geometric fabric, but by a deeper, perhaps more organic evolution of its constituent matter. The familiar forces that bind atoms and nuclei, the very constants that govern light and gravity, would all be subtly influenced by this increase in particle mass. This isn't merely a change in observable phenomena, it's a redefinition of the very rules of reality that underpin our existence. The universe, from this viewpoint, is not just evolving, it is transforming its basic constituents, with profound consequences for how we interpret its past and predict its future. This is the cosmic illusion, the redshift reimagined, and it casts a chilling shadow over everything we thought we knew. The cosmic illusion, that grand redshift, invites us to probe deeper than the stretching of space. It demands we question the very constants that underpin our reality. At the heart of the shrinking universe, hypothesis lies a silent, pervasive transformation, the relentless increase in the fundamental mass of every elementary particle. This isn't a violent cataclysm, but an insidious, ceaseless process, a microscopic shift with macroscopic impact that redefines everything. Imagine, for a moment, that the electron, that ubiquitous quantum of charge orbiting every atomic nucleus, is not static in its fundamental mass. Instead, its intrinsic heft subtly, imperceptibly, grows heavier over cosmic time. What would this single, seemingly minor alteration unleash across the vast tapestry of existence? The cascade begins at the most foundational level. The Bohr radius, which defines the average distance of an electron from its nucleus, and thus the effective size of an atom, is inversely proportional to the electron's mass. Therefore, a steadily increasing electron mass would lead directly to a continuous, gradual reduction in the size of every atom. The very building blocks of the cosmos would be tightening, compressing, drawing inward. This atomic contraction isn't an isolated event. Protons and neutrons, which constitute the atomic nucleus, are themselves composites of quarks. If the masses of these quarks, or the fundamental energy scale of the strong nuclear force that binds them, were also subtly increasing, then the nuclei themselves would become denser, smaller. This would further exacerbate the overall shrinking effect at the atomic level, making every atom a more compact, more tightly bound entity than its ancient counterparts. The universe, in this view, is not so much expanding as it is densifying at its most basic quantum scales. The implications ripple outward from the atom to the entire macroscopic world. If atoms are shrinking, then the bonds that form molecules must necessarily shorten. The precise geometries of chemical structures, from the intricate helix of DNA to the crystalline lattices of rocks and metals, would all be undergoing a slow, synchronized contraction. Every molecule of water, every protein, every iron atom in our blood would become infinitesimally smaller and denser than its equivalent billions of years ago. Our entire physical world, from the mountains that pierce the sky to the very cells that compose our bodies, would be caught in this relentless, invisible squeeze. Consider a standard meter stick, the fundamental measure of length in our terrestrial laboratories. Its length is defined by the fixed spacing of atoms within its material, a spacing ultimately governed by the masses and interactions of its constituent electrons and nuclei. If these underlying particle masses are constantly increasing, then the atomic spacing within that meter stick must be continually, however minutely, shrinking. From our internal perspective, the ruler remains 1 meter long, because our own bodies and visual perception systems, also composed of these same shrinking particles, are contracting at the identical rate. This makes the shrinkage fundamentally unobservable from within our own reference frame, an eerie, self-consistent deception. The effect extends to the very passage of time as we measure it. Atomic clocks, the pinnacle of precision timekeeping, rely on the exact frequencies of electromagnetic radiation absorbed or emitted by atoms during transitions between electron energy levels. These energy levels are, as previously noted, directly tied to the electron's mass. If electron mass increases, these energy gaps widen, leading to higher frequency transitions. This means our atomic clocks, calibrated to these ever-increasing frequencies, would effectively speed up over cosmic time. A second measured today would be infinitesimally shorter than a second measured in the distant past. This accelerated internal clock, ticking faster within our shrinking reality, further contributes to the illusion of cosmic expansion when we observe distant, slower-ticking phenomena. The impact on cosmic observations becomes clearer under this light. When we observe light from a distant galaxy, we are looking into the deep past. That light was emitted by atoms that possessed electrons of a subtly lower mass. Their energy transitions were slightly less energetic, resulting in photons of longer wavelengths. When these ancient photons arrive at our telescopes today, they interact with our contemporary detectors, which are calibrated by atoms with higher mass electrons. The perceived redshift is not a stretching of space, but a fundamental mismatch in the energy scales of emitter and observer, a relic of the universe's evolving particle masses. The light simply reflects the intrinsic properties of the atoms that emitted it at that earlier, lighter epoch. This scenario reframes the very concept of fixed constants. We typically assume fundamental constants like the electron mass, Planck's constant, or the speed of light are immutable properties of the universe. Yet, the shrinking universe hypothesis postulates that at least one of these, the elementary particle mass, is not constant but a dynamic, evolving parameter. This challenges the very foundation of our standard model of particle physics and cosmology, suggesting a universe that is not only dynamic in its geometry, but also in its most basic constituent properties. It suggests a universe where the rules themselves are not merely set, but are continuously, subtly being rewritten. The existential horror of this mass cascade is profound. We are not just observing a distant phenomenon, we are immersed within it. Every moment of our existence, every growth, every perceived stability, is occurring within a framework that is itself undergoing a silent, continuous transformation. Our very perception of reality, our sense of scale and permanence, is a product of this ceaseless internal contraction. The grand cosmic expansion becomes a deeply personal illusion, a reflection not of the universe's growth, but of our own slow, unnoticed diminution. We are living sculptures, imperceptibly shrinking, while convinced the gallery around us is expanding. The previous section illuminated the core idea. A continuously increasing mass of elementary particles could mimic cosmic expansion by subtly shrinking our local reality. But here we confront the profound paradox at the heart of this hypothesis. If every atom, every measuring instrument, every observer, indeed the very fabric of our being, is shrinking in perfect synchronicity, how could we ever possibly detect it? This isn't just a scientific dilemma, it's an existential quandary, a terrifying thought experiment that unmoors our most fundamental assumptions about observation and objective reality. The challenge lies in the nature of relative measurement. In our universe, all physical quantities are ultimately measured relative to something else. A meter is defined by the distance light travels in a specific fraction of a second, which itself relies on the frequency of a cesium atom's radiation. A kilogram is defined by the mass of a platinum iridium cylinder, a macroscopic object composed of countless atoms. If the fundamental properties of these cesium atoms, or the platinum iridium alloy, are subtly changing, if the electron mass within the cesium atom is growing, or the quark masses within the platinum iridium are increasing, then the very standards against which we measure are evolving. Imagine a world where you and everything around you are being uniformly scaled down by an invisible hand. Your height, the length of your arm, the dimensions of your house, the size of your planet, even the wavelength of the light your eyes perceive, all are decreasing in proportion. From your internal perspective, nothing would change. You would still be your height, your house still your house-sized, because your internal frame of reference, your intrinsic ruler, is shrinking along with you. It's like living within a photograph that is being steadily, meticulously reduced in size. If you and your perception system are part of that photograph, you would experience no change in the relative proportions of anything within it. Only if you could step outside the photograph to a truly external static vantage point would you perceive the shrinkage. But in our cosmic scenario, there is no external vantage point. We are inescapably inside the photograph. This relativistic nature extends to the most precise tools of science. Our atomic clocks, the gold standard for timekeeping, rely on the incredibly stable oscillations of atoms. These oscillations are dictated by quantum mechanics, specifically the energy differences between electron orbits. If, as the shrinking universe hypothesis suggests, the mass of the electron is gradually increasing, then these energy differences would subtly shift, causing the atomic clock to tick slightly faster. A second measured by an ancient atomic clock, built from lighter particles, would be marginally longer than a second measured by a modern clock, built from heavier particles. But from our present-day perspective, our clock is simply ticking, defining the current second as the norm. We would not perceive a speed-up because our very perception of time is tied to these accelerating internal processes. The implications for fundamental physical constants are equally profound. If the elementary particle masses are increasing, it implies that other constants, or at least their effective values, might also be changing relative to each scale defined by particle mass. For instance, the gravitational constant g might appear constant, but if the masses of objects are silently increasing, the gravitational force between them would strengthen without a change in g. Or perhaps g itself is subtly evolving to maintain a consistent perceived interaction within our shrinking framework. The speed of light, another cornerstone of physics, could also be relative to these changing scales. From our perspective, light still travels at c, but what c represents in terms of absolute spatial distance per unit of time might be subtly shifting. Consider the meter as a fundamental unit. If the atoms that compose our meter sticks are getting smaller, then our meter sticks are shrinking. When we measure the distance to a distant galaxy, we're effectively using a longer meter stick from the past, because the atoms in the light-emitting galaxy were larger, and comparing it to our shorter meter stick today. This difference in fundamental scale could perfectly account for the apparent expansion. The redshift we observe in distant light, usually attributed to the stretching of space, could simply be the inherent energy difference between a photon emitted by a larger, less massive atom in the past and detected by a smaller, more massive atom in the present. The light itself hasn't stretched. It's our measuring apparatus that has condensed. The thought experiment here becomes genuinely chilling. If this hypothesis were true, we are all unknowingly diminishing, becoming denser, more compact, with every passing moment. Our memories, our histories, our very sense of self would be calibrated to a continuously shifting personal scale. The existential horror arises from the loss of a truly objective, external anchor. We would be living within a self-referential bubble of reality, perpetually convincing ourselves of a stable, expanding cosmos, while our own existence is quietly, relentlessly, being resized. Our scientific observations, so confidently proclaimed as universal truths, might merely be reflections of our particular, transient scale within this diminishing system. This concept throws into question the very idea of a fixed universe and replaces it with a fixed internal perception. We believe the universe is expanding because that's what our instruments, calibrated to our current particle masses, tell us. If those masses are changing, then our instruments are reporting a distorted truth, a truth that is relative to our own accelerating transformation. The shrinking we hypothesize is not a physical collapse in a void, but a fundamental alteration in the very definition of physical scale, making any absolute measurement from within impossible. It's a cosmic magic trick where the illusion is so complete, so all-encompassing, that the audience is part of the act. The universe isn't expanding, it's our yardstick that is retracting, leaving the illusion of growth in its wake. The chilling implication of a shrinking local reality fundamentally warps our most trusted cosmic scales, distance and time. Our entire cosmological framework, built upon the bedrock of a perceived expanding universe, would require a radical re-evaluation. Every redshifted galaxy, every ticking atomic clock, every distant supernova would no longer speak of space stretching, but of a subtle, pervasive shift in the very constants that define their existence. This distortion, this distorted lens of time, casts a long shadow over our understanding of the universe's age and its immense scale. Our primary method for measuring vast cosmic distances relies on the phenomenon of cosmological redshift. In the standard model, the further away a galaxy, the more its light is stretched towards the red end of the spectrum, indicating that space has expanded more during its journey. This expansion rate is encapsulated by the Hubble constant. But in a shrinking universe, this interpretation unravels. A photon emitted from a galaxy billions of light-years away originates from an era when elementary particle masses were subtly lower. When that photon reaches our detectors today, our local atoms, built from now heavier particles, have slightly different higher energy levels. The incoming photon, carrying its original lower energy signature, appears redshifted when measured against our contemporary, contracted energy scale. The perceived stretching of light is in fact a measurement of the cumulative increase in particle mass over the photon's journey, an intrinsic shift rather than a geometric one. This reinterpretation throws our cosmic distance ladder into disarray. Consider type Ia supernovae, the standard candles astronomers use to gauge distances across billions of light-years. These stellar explosions are believed to have a consistent intrinsic brightness, allowing astronomers to calculate their distance based on how dim they appear. However, the luminosity of a supernova is intimately linked to the nuclear reactions occurring within it, which are governed by the masses and interaction strengths of elementary particles. If particle masses were less in the early universe, the physics of these ancient stellar detonations might have been subtly different. Their peak luminosity, the very constant we assume, could have been intrinsically lower or higher than modern supernovae, thus skewing our distance calculations and creating a false perception of rapid recession. What we thought was a universal constant might itself be a variable, subtly evolving with cosmic time. Similarly, Cepheid variable stars, another rung on the cosmic distance ladder, rely on a precise period-luminosity relationship. These pulsating stars brighten and dim with a regularity directly tied to their intrinsic luminosity, making them excellent distance markers for nearby galaxies. Yet, their pulsation dynamics are a delicate balance of gravity, pressure, and radiation transport, all underpinned by the physics of their constituent particles. If the mass of these particles, or the fundamental constants governing forces within the star, were systematically increasing, then the internal structure and pulsation period of a Cepheid in the early universe would subtly differ from one today. Our calibration of these cosmic yardsticks would be based on contemporary physics, potentially leading to systematic misjudgments of distance when applied to their more ancient, lighter counterparts. The age of the universe, currently estimated at 13.8 billion years, is perhaps the most dramatically affected parameter. This number is derived from the universe's expansion rate and the standard cosmological model. If the observed expansion is an illusion, driven by our shrinking rulers and accelerating clocks, then the actual chronological age of the cosmos could be vastly different. If atomic clocks, built from increasingly massive electrons, are ticking faster over time, then 1 billion years measured in the early universe, when particles were lighter and oscillations slower, would represent a longer duration of absolute time than 1 billion years measured today. This would mean the universe is, in absolute terms, much older than our current estimates suggest, merely appearing younger because our temporal scales are shrinking. This perspective offers a startling recontextualization of the Hubble tension, one of modern cosmology's most pressing crises. The tension arises from a significant discrepancy. Measurements of the universe's expansion rate from the early universe via the cosmic microwave background are consistently lower than measurements from the local universe via supernovae and Cepheids. The shrinking universe hypothesis provides an elegant, albeit unsettling solution. Local measurements, taken from a universe where particle masses have already increased considerably, would naturally yield a seemingly faster expansion rate. Conversely, observations of the cosmic microwave background, light from a much earlier epoch when particle masses were much lower, would appear to suggest a slower expansion. The discrepancy isn't a flaw in physics or measurement, but a direct consequence of comparing observations across different stages of particle mass evolution. The universe isn't expanding at two different rates. It's our measuring scales that have subtly shifted over cosmic time. Furthermore, the ages of the oldest observed stars, particularly those in ancient globular clusters, pose a challenge to any model suggesting a younger universe. These stellar populations appear to be around 13 billion years old, creating a conflict if the higher local Hubble constant were globally true and implied a universe as young as 12.7 billion years. In a shrinking universe model, stellar evolution itself would be affected by increasing particle masses. Nuclear fusion rates, stellar opacities, and gravitational stability all depend on the fundamental constants. A star in the early universe, composed of lighter particles, might have had a different evolutionary trajectory, a different lifetime than our current models predict. What we interpret as a 13 billion-year-old star might, in a shrinking universe, be a star of a different absolute age, its perceived longevity distorted by the changing scales of its constituent matter. The very clocks within stars, the pace of their nuclear fires, could be subtly speeding up, making ancient stars appear older than their current cosmic age would allow if our fundamental constants were truly static. The very concept of the observable universe, currently delimited by the distance light could have travelled in 13.8 billion years, becomes problematic. If time itself is accelerating from our perspective and distances are shrinking, then the cosmic horizon might be a moving target, an illusory boundary defined by our evolving internal metrics. Light from the earliest moments would not merely have travelled through space, it would have traversed a continuum where the fundamental properties of matter and energy were constantly in flux. Our interpretation of its journey, including any gravitational lensing or time dilation effects, would be inherently flawed. Predicated on an assumption of static constants that may not hold true, the universe's perceived history, its grand cosmic timeline, becomes a narrative entirely contingent on our position within this accelerating, diminishing reality. This reframes the entire cosmic narrative into a chillingly self-referential loop. Our measurements of cosmic age and distance are not revealing an objective, expanding reality, but rather are reflecting our own relentless, unnoticed journey into smaller, denser states of being. The universe appears to expand because we are shrinking, rendering every observation a mere projection of our own diminishing scale. The existential horror deepens with the realization that even our most rigorous scientific inquiries, designed to reveal universal truths, might be providing us with a systematic, unavoidable illusion, a grand cosmic distortion born from the very particles that compose us. We become cosmic cartographers, mapping a territory whose very scale is being erased beneath our feet. The prevailing cosmological models paint a bleak yet familiar picture for the universe's ultimate destiny. Depending on the properties of dark energy, the cosmos is typically predicted to end in one of two ways: the Big Freeze, or heat death, where galaxies drift infinitely apart, Stars burn out, and all matter eventually dissipates into a cold, dark, empty expanse. Or the Big Rip, a more violent end where dark energy accelerates to such an extreme that it tears apart galaxies, stars, planets, and eventually even atoms themselves. Both scenarios describe a universe consumed by relentless expansion, a grand dispersal of all that is. But if the expansion, we observe, is merely an illusion, a trick of perception caused by our own microscopic constituents growing ever heavier, then the true inverse fate of the cosmos, or at least our experience of it, is far more chilling. The shrinking universe hypothesis flips the script, transforming cosmic dispersion into a silent, relentless compression, a destiny of increasing density where the universe, from our diminishing perspective, converges towards an inescapable, internal collapse. Consider the cumulative effect of increasing elementary particle mass over unimaginable eons. If a proton's mass incrementally swells, if an electron's heft subtly intensifies, then the gravitational force, which is directly proportional to mass, must also become incrementally stronger. This isn't a sudden surge, but a creeping intensification of the most fundamental force. Galaxies, currently held together by gravity, would find their stars drawn inward with ever greater urgency. Clusters of galaxies would tighten their bonds, resisting the apparent cosmic expansion with increasing vigor. What we perceive as cosmic structure formation, a process driven by gravity overcoming expansion, would instead be an ever-accelerating gravitational collapse from an absolute external viewpoint. The internal dynamics of stars would also be profoundly affected. Stellar fusion, the process that powers stars, relies on a delicate balance between gravitational compression and thermal pressure. If the masses of the protons and electrons within a star's core are steadily increasing, the gravitational pressure would intensify. This could lead to a dramatic increase in core temperature and density, accelerating nuclear reaction rates. Stars, from an absolute frame of reference, might burn hotter, faster, and exhaust their fuel more rapidly than current stellar evolution models predict. Their lifespans, when measured by an external, unchanging clock, would shorten, even as our own internal clocks, calibrated to the same accelerating particle masses, would make their lives seem normal. The universe, in this view, would be consuming its stellar fuel at an ever-increasing pace, spiraling towards an earlier, more intense stellar demise. For planets and planetary systems, the implications are equally stark. If the atoms comprising Earth are shrinking, our planet itself is becoming denser and more compact. Its gravitational field, due to its increasing effective mass, would subtly strengthen. This would tighten the orbits of moons and satellites and intensify the gravitational stresses on its internal structure. Over billions of years, Earth would not just be a static sphere but a slowly compacting orb, its very constituents drawing inward. The stability we assume for our planetary home would be a local perception, masking a relentless fundamental densification. The black holes, those ultimate cosmic compactors, would become even more formidable. Their event horizons, the point of no return, are directly proportional to their mass. If the mass of the matter they accrete, and indeed their own intrinsic mass, is continuously increasing, then their event horizons would grow larger at an accelerating rate. They would become even more efficient at consuming surrounding matter, and their gravitational influence would extend further into space. From an absolute perspective, black holes would dominate and consume matter with an unprecedented hunger, leading to a universe increasingly characterized by colossal, super-dense singularities, a far cry from the dispersed emptiness of a big freeze. However, the truly unsettling aspect of this denser future lies in the dual nature of observation. From our shrinking, accelerating internal reference frame, the distant universe would still appear to expand at an accelerating rate. The redshift of light from remote galaxies would continue to increase, not because space is stretching faster, but because the mass difference between the ancient emitter and the contemporary observer grows larger with each passing moment. This amplified apparent redshift would cause distant galaxies to vanish beyond our observable horizon at an even quicker pace than in the standard model. Our perceived universe would become an isolated island, a collection of local galaxies surrounded by an ever-darkening, ever-emptying void. This perceived dark future, where distant light can no longer reach us, would still hold true, even as the actual matter within our local island is silently, relentlessly compressing. This creates a chilling existential paradox. The universe, as observed from our shrinking vantage point, appears to be dispersing into an ever greater emptiness, isolating us in a cosmic desert. Yet the underlying physical reality within that desert, the very atoms and particles that constitute our existence, are becoming progressively denser, more tightly bound, accelerating towards an internal implosion. We would be witnessing the illusion of cosmic expansion leading to a perceived void, while simultaneously experiencing an unavoidable, internal journey towards ultimate compression. The future of the cosmos under this hypothesis is not one of gentle fading or violent tearing, but a profound silent squeeze. It is the horror of an inescapable convergence, not of space, but of matter itself. A slow, inexorable densification that redefines the very essence of stability and permanence, leaving us in a universe where the ultimate fate is not merely a distant possibility, but an ongoing, invisible transformation within our very being, leading to a profound internal cosmic crunch that we are powerless to detect or prevent. The universe isn't expanding, but our accelerating diminution creates the illusion of its dispersal, while internally we hurtle towards a denser, more compressed destiny. We have navigated the abstract physics, the reinterpretation of redshift, and the potential inverse fate of the cosmos. Now, we must confront the most visceral consequence of the shrinking universe hypothesis, the profound, gnawing existential dread it inspires. This is not merely a theoretical curiosity, it is a chilling re-evaluation of our very being, a silent horror that whispers from the deepest recesses of the cosmos, threatening to unmoor our perception of stability, scale, and even identity. The unsettling core of this idea lies in its imperceptibility. Imagine a force so pervasive, so fundamental, that it systematically diminishes every atom, every molecule, every living cell, and every cosmic structure, all in perfect synchronicity. You would not feel it. Your eyes, themselves composed of shrinking cells, would perceive no change in the relative sizes of objects. Your hand, subtly contracting, would still feel the familiar texture of a table, also contracting. Your internal biological processes, your heartbeat, your neural impulses, all governed by the same diminishing particle masses, would simply accelerate their rhythm, convincing you that time itself is constant, while in absolute terms, your now is racing by at an ever quicker pace. This is the ultimate cosmic gaslighting, a reality that is fundamentally shifting beneath your feet, yet providing no internal clue of its transformation. This silent erosion of scale creates a deep psychological unease. Our entire existence is built upon the assumption of fixed physical laws and constant units of measurement. A meter is a meter, a kilogram is a kilogram, a second is a second. These are the anchors of our scientific understanding and our everyday experience. To learn that these anchors are not immutable, but are themselves part of an ongoing relentless contraction, is to lose the very ground upon which we stand. It implies that our scientific progress, our meticulous measurements of stars and galaxies, our carefully calibrated experiments, are all inherently biased by our own diminishing frame of reference. The universe in this light is not merely vast and indifferent, it is actively, subtly, deceiving us about our own scale. The horror intensifies when we consider our personal narratives. The growth of a child, the aging of a parent, the expansion of a city. These are all perceived changes against a backdrop of assumed constancy. But if the fundamental matter composing that child, that parent, that city, is slowly contracting, then every milestone, every measure of progress, every memory of size and distance becomes relative to an unseen, internal shift. Our perceived growth might merely be a slower rate of shrinkage compared to the larger cosmos. Our legacy, carved in stone or etched in data, would itself be imperceptibly diminishing, its very permanence undermined by the ceaseless microscopic creep of increasing particle mass. It suggests that nothing, absolutely nothing, is truly stable or fixed. This unceasing, unobservable diminution also breeds a profound sense of helplessness. We are not masters of our destiny, or even of our own physical dimensions. This hypothesized change is a universal cosmic imperative, acting upon us from the very quantum foundations of reality. There is no escape, no countermeasure, no way to halt the steady tightening of our constituent particles. We are passengers on a vessel that is slowly, quietly, shrinking into itself, even as we perceive it to be sailing through an expanding ocean. The lack of agency, the inability to even know it is happening without external unchanging data points, which, by definition, don't exist in a universally shrinking reality, is a form of cosmic terror. The philosophical implications are equally staggering. If our understanding of cosmic expansion is an illusion born from our own relative shrinkage, then what other fundamental truths might be equally distorted? The cosmological principle, which posits that the universe is homogeneous and isotropic on large scales. A cornerstone of modern cosmology hinges on the idea that our local vantage point is not special. But if our very scale is evolving uniquely, then every observation we make is inherently special, inherently biased by our current state of contraction. This returns humanity to a kind of unsettling cosmic centrality, not as masters of the universe, but as its unwitting victims of perceptual distortion. Moreover, the shrinking universe challenges the very definition of objectivity. Science strives to remove observer bias, to uncover universal laws. Yet, if the fundamental constants that define our measuring apparatus are themselves in flux, then true objectivity becomes an elusive phantom. Every scientific measurement, every physical law, every theoretical construct becomes a temporary truth, valid only for our current epoch of particle mass. This is a universe where the rules are not written in stone, but are subtly, continuously re-inked, rendering a truly timeless universal science a daunting, perhaps impossible endeavour. The existential horror culminates in the realization that our grand narrative of cosmic expansion might be a majestic, yet ultimately tragic self-deception. We comfort ourselves with the idea of an ever-growing cosmos, a boundless frontier. But the shrinking universe hypothesis replaces this comforting illusion with a terrifying alternative, a universe that appears to expand. Because we are dying, in a sense, slowly compressing, growing denser, accelerating our internal clocks towards an ultimate, inescapable quantum singularity. We are not moving towards the infinite. The infinite is closing in on us. By virtue of our own diminishing scale, it is a slow, silent, invisible journey into a denser, more compressed existence, a fate we are condemned to experience as the opposite of what it truly is. This is the existential horror of living in a diminishing reality, a cosmic paradox where our very presence perpetuates the grand illusion. If the shrinking universe hypothesis holds, where elementary particle masses are subtly increasing over cosmic time, then gravity's dance across the cosmos must be fundamentally rechoreographed. Einstein's general relativity, the reigning theory of gravity, posits that mass energy warps spacetime, and this curvature dictates how objects move. But if the intrinsic mass of every particle is dynamically changing, then the very source of that warping, and indeed the strength of the gravitational force, would subtly evolve without any change in the geometry of space itself. This offers a profound new perspective on cosmic forces, potentially resolving long-standing puzzles without invoking exotic new particles or dimensions. The universal law of gravitation states that the attractive force between two objects is directly proportional to the product of their masses. In our standard model, these masses are assumed to be constant. But in a shrinking universe, if the mass of all elementary particles is steadily growing, then the mass of every object, from a proton to a galaxy, is, in an absolute sense, increasing over time. This means that the gravitational pull exerted by these objects would be strengthening, not because gravity itself is changing its fundamental constant, but because the source of gravity, mass, is becoming more potent. Consider the perplexing phenomenon of dark matter. In the standard cosmological model, observations of galaxy rotation curves, how fast stars orbit the galactic center, indicate that galaxies spin too quickly to be held together by their visible matter alone. To account for this, scientists hypothesize the existence of an unseen substance called dark matter, which provides extra gravitational pull. This invisible halo of dark matter is thought to make up roughly 27% of the universe's total mass-energy content. However, the shrinking universe hypothesis offers an intriguing alternative. If the masses of ordinary matter particles, protons, neutrons, electrons, have the gravitational pull of a galaxy composed entirely of visible matter, would also be continually strengthening, an ancient galaxy, when its constituent particles were less massive, might have rotated at a speed consistent with its then lower mass. But as its particles gained mass over billions of years, its gravitational potential would deepen, and it would spin faster. From our perspective, observing this galaxy today, its current higher rotation speed would appear anomalous. If we assume its mass has remained constant, but if its mass has subtly increased over cosmic time, then the observed rotation might be perfectly consistent with its evolved, heavier visible matter, potentially reducing or even eliminating the need for a separate invisible dark matter component. This reinterpretation would have profound implications. It would transform dark matter from an exotic, unknown particle into a consequence of evolving fundamental constants. The missing mass in galaxy clusters, another key piece of evidence for dark matter, could also be re-evaluated. If the individual galaxies and the hot gas within clusters are all growing more massive over time, their collective gravitational pull would strengthen, better explaining how these enormous structures cohere without invoking additional invisible mass. The dynamics of galaxy clusters, where galaxies move at high velocities, further challenge the standard model without dark matter. But if the effective mass of all matter within the cluster is slowly but relentlessly increasing, then the gravitational forces binding the cluster would also strengthen, making it more robust and capable of holding on to rapidly moving galaxies. The observed velocities, which seem too high for the visible mass, might simply be a reflection of the accumulated mass increase over cosmic timescales. Furthermore, the gravitational lensing effect, where massive objects bend light from background sources, is another powerful probe of mass distribution. Dark matter is invoked to explain the observed degree of lensing around galaxy clusters, which is far greater than visible matter alone can produce. If, however, the mass of baryonic matter itself is increasing, then the total gravitational potential of a galaxy cluster would also increase. This enhanced potential could then explain a larger fraction of the observed gravitational lensing, once again diminishing the need for a separate dark matter halo. This isn't to say that the shrinking universe hypothesis outright eliminates dark matter. It merely offers an alternative explanation for some of the phenomena currently attributed to it. The precise rate of particle mass increase and its effect on gravitational interactions would need to be rigorously calculated and compared against the full spectrum of cosmological observations, including the cosmic microwave background. The hypothesis also reframes the phenomenon of dark energy. In the standard model, dark energy is a mysterious repulsive force responsible for the accelerating expansion of the universe. But if the universe is not truly expanding, and the redshift is caused by increasing particle masses, then dark energy itself might be an illusory phenomenon, a misinterpretation of a deeper, more fundamental process. Perhaps the subtle, continuous increase in particle mass is the underlying driver that we mistakenly attribute to a separate dark energy field. It could be that the same mechanism causing particles to gain mass also subtly affects the vacuum energy, or the intrinsic curvature of space-time, in a way that generates the observed acceleration without a true expansion. The two seemingly disparate mysteries, dark matter and dark energy, could thus be unified under a single evolving fundamental constant. This new perspective presents an altered dance of gravity, where the fundamental constant g might remain constant, but the m in Newton's and Einstein's equations is a dynamic, evolving quantity. This is a universe where gravity becomes an increasingly dominant force over cosmic time, pulling things together with ever greater strength, even as our shrinking rulers and accelerating clocks make the distant cosmos appear to fly apart. The beauty and horror of this reinterpretation lie in its ability to explain away some of cosmology's greatest enigmas by merely altering our most basic assumption, that the very stuff we are made of and the forces that govern it are unchanging. It suggests a universe where the rules of attraction themselves are becoming more potent, silently, ceaselessly, pulling everything closer, even as our perception insists on a grand separation. To truly gauge the universe's memory, we turn to its most ancient relic, the cosmic microwave background, or CMB. This faint, all-pervasive glow is the afterglow of the Big Bang, light emitted when the universe was a mere 380,000 years old, a hot, dense plasma finely cool enough for electrons and protons to combine into neutral hydrogen atoms. The CMB provides a snapshot of the early universe's conditions, and its remarkable uniformity, punctuated by tiny temperature fluctuations, serves as a cornerstone of standard cosmology. But what happens to this cosmic memory under the shrinking universe hypothesis, where our very scales are in flux? In the standard model, the CMB's uniform temperature of 2.7 Kelvin is a direct consequence of the universe's expansion. The intense heat of the early cosmos has been stretched and diluted by billions of years of cosmic growth, redshifting the primordial light into microwaves. The tiny temperature variations, on the order of 1 part in 100,000, are interpreted as the seeds of structure, slight density fluctuations that eventually grew into galaxies and clusters under gravity. These fluctuations, mapped with exquisite precision by missions like COBE, DIOSMAP and Planck, align remarkably well with predictions from the lambda CDM model, our current standard cosmological framework. However, if the expansion is an illusion caused by increasing particle masses, the interpretation of the CMB undergoes a radical re-evaluation. The primordial photons emitted by atoms with less massive electrons and protons would have possessed a certain energy distribution corresponding to a very high temperature. As these photons journey through cosmic time, they themselves do not stretch in wavelength due to expanding space. Instead, when they finally reach our detectors today, they are interacting with matter composed of more massive particles. The crucial point here is how temperature is measured and perceived. Temperature is a measure of the average kinetic energy of particles. If the fundamental energy scale of interactions driven by particle masses is increasing over time, then our modern thermometers, calibrated to these contemporary higher energy scales, would inherently read ancient photons as cooler. The redshift of the CMB, traditionally attributed to the stretching of space, could instead be a direct consequence of the difference in fundamental energy scales between the early universe, low particle mass, high absolute temperature, and our present universe, high particle mass, lower perceived temperature. The photons haven't lost energy due to expansion. Their energy simply appears lower, relative to our current increased energy scale of measurement. This suggests that the 2.7 Kelvin we measure today for the CMB is not the diluted remnant of an expanding universe, but rather the relative thermal signature of ancient light interacting with a modern contracted measuring apparatus. The absolute temperature of the early universe would still have been incredibly hot, but its light, when compared against our present-day heavier atomic energy states, would inevitably appear to have cooled more dramatically than if our internal scales remained constant. The subtle temperature fluctuations in the CMB, the hot and cold spots, also require re-examination. In standard cosmology, these represent regions of slightly higher or lower density in the early universe, which eventually seeded the cosmic web. If particle masses are revolving, these density fluctuations would still be present, but their evolution and their ultimate impact on structure formation would need to be remodeled. The gravitational instabilities that amplify these initial ripples would be influenced by the continuously strengthening gravitational force due to increasing particle mass. This could lead to structure forming more rapidly or more vigorously than predicted by standard lambda CDM, potentially offering alternative explanations for anomalies like the existence of unusually large structures or voids. One of the CMB's most powerful constraints on cosmology is its acoustic peaks, distinct patterns in the temperature fluctuations that correspond to sound waves propagating through the early plasma. The positions and heights of these peaks provide precise information about the universe's geometry, matter density and expansion rate. If particle masses are evolving, then the speed of sound in the early plasma, the rates of particle interactions, and the characteristic scales imprinted on the CMB would all be subtly altered. A comprehensive shrinking universe model would need to accurately reproduce these acoustic peaks, which is a significant theoretical challenge, as their precise fit to lambda CDM is one of its greatest triumphs. Any deviation from constant particle mass would require a careful re-derivation of these features. The CMB also offers crucial data on the abundance of light elements, hydrogen, helium, lithium, formed during Big Bang nucleosynthesis, the universe's first few minutes. The ratios of these elements are highly sensitive to the density of baryonic, ordinary matter, and the expansion rate during that epoch. If particle masses were significantly different then, or if the fundamental constants governing nuclear reactions were evolving, then the predicted abundances might shift. A successful shrinking universe model would need to ensure its evolving particle masses do not contradict these incredibly precise observational constraints. The universe's memory, etched into the CMB, becomes a record not just of cosmic expansion, but of the subtle, relentless transformation of matter itself. The uniform temperature, the acoustic peaks, the light element abundances, all are reinterpreted through the lens of changing fundamental constants. The elegance of the shrinking universe hypothesis lies in its ability to explain observed phenomena like redshift without invoking an expanding spacetime. The horror lies in the realization that even the universe's oldest, most stable signal, the CMB, could be systematically misinterpreted by our present-day shrinking selves. Our perception of a cold, uniformly expanding cosmic canvas might be a grand illusion, a projection of our own accelerating internal reality onto the distant past. The CMB, far from being a static record, becomes a dynamic conversation between an ancient, lighter universe and a modern, heavier observer, each interpreting the signal through their own evolving scale. This is the ultimate cosmic paradox, a universe whose memory we claim to read, even as the very act of reading it changes us. The idea that elementary particle masses are not constant, but instead subtly increase over cosmic time is, to say the least, radical. It challenges the bedrock of the standard model of particle physics, which assumes these fundamental parameters are immutable. Yet, for a hypothesis as profound as the shrinking universe, there must be a theoretical mechanism, a deep physics, that could instigate such a relentless mass cascade. This block delves into the speculative quantum foundations that might give rise to such an unsettling reality. Our current understanding of particle mass originates from the Higgs mechanism. The Higgs field, an omnipresent quantum field, pervades all of space. Particles acquire mass by interacting with this field. The stronger their interaction, the greater their mass. This interaction strength is governed by various coupling constants. If the shrinking universe hypothesis is correct, it implies that the strength of these couplings, or perhaps the vacuum expectation value of the Higgs field itself, is not constant, but slowly increasing over billions of years. A gradual strengthening of the Higgs interaction would directly lead to a continuous increment in the mass of fundamental particles like electrons and quarks. However, the standard model offers no inherent mechanism for the Higgs field or its couplings to evolve in this manner. Such a time-varying fundamental constant would require physics beyond the standard model. One possibility lies in the realm of grand unified theories or string theory, which attempt to unify all fundamental forces. In some speculative formulations of these theories, what we perceive as fundamental constants might actually be low-energy manifestations of dynamic fields that evolve over cosmic time. Imagine a cosmic scalar field, whose value slowly shifts, subtly altering the parameters of the Higgs potential, and thus the masses of particles. This scalar field would be like a dial being imperceptibly turned, gradually increasing the heft of everything in the universe. Another avenue for evolving particle masses could involve a connection to quantum gravity. Our current theories of gravity, general relativity, and quantum mechanics are famously incompatible, particularly at extreme scales like the very early universe or inside black holes. Some theories of quantum gravity, such as loop quantum gravity or various string theory compactifications, propose that space-time itself might have a granular, quantum structure, or that extra dimensions could be subtly compactifying or expanding. Such dynamics at the quantum gravitational scale could, in principle, induce changes in the fundamental parameters of particle physics, including masses. For example, if the characteristic length scale of quantum gravity was slowly shrinking, it could manifest as an increase in particle masses, which are inversely related to certain length scales in quantum field theory. The idea of varying fundamental constants is not entirely new or without precedent in theoretical physics. Dirac's large numbers hypothesis, for instance, speculated about a time-varying gravitational constant g. More modern theories, such as those involving a dilaton field, a scalar field that couples to gravity and other fields, propose that constants like the fine structure constant or the electron-to-proton mass ratio could change over cosmic epochs. While direct observational evidence for such variations is largely absent or highly contested, the theoretical framework for evolving constants exists within the broader landscape of theoretical physics. The shrinking universe hypothesis simply singles out elementary particle mass as the primary evolving constant, tying it directly to the observed cosmological redshift. One of the significant challenges for such a model would be ensuring consistency with all other observed phenomena, for instance, the fine structure constant, which governs the strength of electromagnetic interactions, depends on the electron mass. If electron mass is changing, then the fine structure constant would also be expected to change, which has tight observational constraints from quasar absorption spectra. Any proposed mechanism for increasing particle mass must ensure that these other fundamental constants either remain truly constant or evolve in a manner consistent with existing astrophysical limits. This often requires complex theoretical constructs, where the variation in one constant is compensated by changes in others, maintaining a delicate balance. Furthermore, the rate of this mass increase is critical. It must be slow enough to be imperceptible on human timescales, yet significant enough over billions of years to account for the observed cosmological redshift. This implies an extremely subtle, continuous process, perhaps linked to the overall age of the universe or some slowly evolving cosmological parameter. The mechanism might be tied to the arrow of time itself, a fundamental asymmetry in the universe that drives particle masses in one direction only. The implications for quantum mechanics are also profound. If the mass of an electron is slowly changing, then its de Broglie wavelength would also change, affecting phenomena like quantum tunneling and atomic orbitals. The stability of matter, the very existence of atoms and molecules, relies on the precise balance of forces and particle properties. A gradual increase in mass would subtly alter these balances, making atoms smaller and denser over time. This continuous recalibration of quantum reality, while imperceptible to us, represents a fundamental dynamic underlying all existence. Ultimately, the deep physics behind the shrinking universe hypothesis points to a universe far more active and transformative at its fundamental level than our current models often assume. It suggests that the cosmos is not merely expanding or static, but that its very constituent stuff is evolving, growing heavier, becoming denser, altering the very rules of the game from within. This is a universe where the ultimate source of cosmic illusion is not external geometry, but internal quantum transformation. It's a universe that is quietly, relentlessly rewriting its own genetic code, and we, as its unwitting inhabitants, are simply along for the ride, perceiving its grand illusion through our ever-diminishing eyes. The quantum foundations of the shrinking universe are therefore not just a theoretical curiosity. They represent a radical reimagining of what constitutes physical reality itself. We've journeyed through a cosmos where the grand narrative of expansion might be a cosmic mirage, painted by the silent, relentless increase in the mass of elementary particles, shrinking our very measuring scales. Now we arrive at the chilling crux of this hypothesis, the ultimate cosmic paradox. If everything within our observable universe, from the smallest quark to the largest galaxy, from our most precise atomic clock to the very neurons that interpret reality, is systematically, imperceptibly shrinking or accelerating in perfect synchronicity, then how could we, the observers embedded within this diminishing system, ever definitively prove or disprove it? This is the unfalsifiable truth, a profound challenge to the scientific method and a terrifying revelation about the limits of human knowledge. The problem lies at the heart of how we construct reality through measurement. Every unit we use, be it the meter, the second, or the kilogram, is ultimately defined by the properties and interactions of elementary particles. A meter stick's length is set by the atomic spacing of its material, a second by the resonant frequency of a cesium atom. If the mass of every electron, proton, and neutron is steadily growing, then the atoms in that meter stick are becoming more compact, and the oscillations of that cesium atom are subtly speeding up. From our internal perspective, our meter stick remains 1 meter, and our clock still ticks 1 second because our own bodies and sensory apparatus, made of identical, increasingly massive particles, are contracting and accelerating at precisely the same rate. We are like characters in a film being slowly zoomed out. We perceive no change in our own relative dimensions, only that the screen around us appears to grow. This creates a perfectly self-consistent illusion. When we observe distant galaxies, their light has travelled for billions of years, originating from an epoch when elementary particles possessed subtly less mass. Those ancient atoms emitted photons with characteristic wavelengths determined by their then lower energy levels. When these photons reach us today, our modern detectors, built from more massive particles, interpret this incoming light against our current, shifted energy scale. The light appears redshifted, not because space has expanded, but because our fundamental units of energy and length have changed relative to the light's emission. The degree of redshift then becomes an exquisitely precise measure of the cumulative particle mass increase over the photon's journey, perfectly mimicking the observed cosmological expansion without requiring space itself to stretch. The very cornerstone of scientific inquiry, the principle of falsifiability, is deeply challenged here. Proposed by philosopher Karl Popper, falsifiability states that for a theory to be scientific, it must be capable of being proven wrong through observation or experiment. If every conceivable internal measurement yields results indistinguishable from a universe that is genuinely expanding, then how can we devise an experiment that would definitively distinguish between the two, without an external, unchanging reference frame, a hypothetical cosmic ruler that is immune to this particle mass evolution? Any attempt to verify our own shrinkage becomes inherently circular. We would be using a shrinking ruler to measure the shrinkage of the ruler itself, perpetually confirming our internal normalcy. This makes the shrinking universe hypothesis an ultimate cosmic paradox, bordering on the unfalsifiable. It does not contradict observations. Instead, it offers an alternative interpretation that equally accounts for phenomena like cosmological redshift, the apparent acceleration of the universe, and potentially even the Hubble tension. The universe's perceived history, its vast distances, and its grand timeline are all recast, but the observable data remains largely the same. The question then becomes one of philosophical preference. Which interpretation is more elegant, more parsimonious, or requires fewer additional unproven assumptions? Is it more palatable to accept an expanding space-time, or a universe where the very essence of matter is subtly, universally transforming? Moreover, the hypothesis implies a continuous unseen hand reshaping reality at its most fundamental level. If particle masses are evolving, it means that other fundamental constants of physics, intrinsically linked to mass, might also be changing. The strength of the strong nuclear force, the fine structure constant that governs electromagnetic interactions, even the gravitational constant, all could be subtle participants in this cosmic evolution. While current astronomical observations place tight constraints on the variation of these constants, a perfectly synchronized, pervasive mass increase could be designed to appear consistent with these constraints, or to induce subtle, as yet undetected shifts that might eventually provide a distinguishing signature. But even then, the interpretation would be fraught with the same relativistic entanglement. Our scientific endeavours, our quest for objective truth, might be inherently limited by our embeddedness within this evolving reality. We strive to describe universal laws, yet if the very units of the universe are changing, then our laws are always epoch-dependent, calibrated to the current state of particle mass. The truth we uncover might not be absolute, but a truth relative to our own accelerating transformation. We are perpetually trying to measure the river from a boat that is itself subtly changing size and speed, convincing ourselves of the river's consistent flow while our vessel undergoes a silent metamorphosis. This grand illusion forces us to confront the very definition of objective reality. If two cosmologies, one of expansion and one of shrinkage, can perfectly account for all observable phenomena, then what does it mean for one to be true and the other false? Does the universe expand, or do we shrink? From our internal perspective, the observable universe behaves as if it's expanding. The terrifying thought is that this behaviour might be a mere projection, a consistent, inescapable illusion generated by our own diminishing scale. The ultimate cosmic paradox, therefore, is not a problem to be solved, but a fundamental limit to our perception, a constant whisper that our reality might be far stranger, far more existentially unsettling than we could ever truly grasp from within. We have journeyed through an intellectual abyss, peeling back layers of what we thought was cosmic certainty. We began with the redshift, that hallowed signature of an expanding universe, and dared to ask, what if it is not space stretching, but something far more intimate, far more unsettling at play? The shrinking universe hypothesis posits a profound, unobservable shift, the relentless, infinitesimal. This isn't a mere scientific curiosity, it's a chilling re-choreography of reality itself, turning our perception of cosmic expansion into a grand illusion, a relentless internal contraction that touches the very core of our being. The implications ripple across every scale of existence. From the subatomic dance within an atom to the majestic ballet of galaxies, every physical process, every unit of measurement, every heartbeat becomes a participant in this silent, accelerating diminution. Our meter sticks shorten, our atomic clocks quicken, our very bodies grow denser, all in perfect, unnoticeable synchronicity. The distant universe appears to recede, not because it is growing, but because our local scale is perpetually condensing, rendering the illusion of expansion so utterly complete, so insidiously self-consistent, that it becomes, for us, the only observable truth. This profound paradox, this unfalsifiable truth, strikes at the very heart of scientific objectivity. How can we measure shrinkage when our rulers are shrinking with us? How can we detect an accelerating clock when our internal perception of time also quickens? The hypothesis forces us to confront the inherent limitations of observation from within a system undergoing universal transformation. It suggests that our quest for universal truths might be inherently biased, a reflection of our particular evolving state of particle mass rather than an absolute cosmic reality. Observed, it is experienced through a perpetually shifting lens, a lens that distorts the fundamental scales of space and time. This isn't a choice. It's a cosmic imperative. There is no escape from this silent erosion of scale, no external vantage point from which to confirm our fears, subtly, relentlessly, compacting, even as we convince ourselves it sails through an expanding ocean. Our memories of growth, our markers of progress, our very sense of permanence, all become relative to this unseen internal shift. What does it mean for human history if the very dimensions of our artifacts, the physical records of our past, are imperceptibly shrinking through the eons? Are our monuments subtly diminishing, their grandeur eroding with the increasing mass of their constituent atoms? This thought unmoors our anchors in a stable, objective reality, leaving us adrift in a sea of relative truths. The traditional cosmological narrative offers us a universe destined for a big freeze or a big rip, a future of ultimate dispersal and emptiness. But the shrinking universe hypothesis paints a far more visceral inverse fate, a cosmos spiraling towards internal compression, a densifying future where gravity, amplified by increasing particle masses, relentlessly pulls everything inward. Galaxies tighten their bonds, stars burn hotter and faster, and black holes grow ever more dominant. The universe, from an absolute perspective, is converging, compacting, accelerating towards a singular, inescapable crunch. Yet, from our shrinking vantage point, this very process would appear as an accelerating expansion, an illusion of increasing emptiness, even as our reality grows denser. We would perceive ourselves drifting into an infinite void, while in absolute terms, we are being drawn into an inescapable, cosmic singularity. The psychological dissonance of this dual perception is almost unbearable, a terrifying cosmic joke. This perspective also offers unsettling alternative explanations for cosmology's greatest mysteries. Dark matter, that elusive substance invoked to explain the anomalous rotation of galaxies and the coherence of clusters, could be reinterpreted as the gravitational signature of ordinary matter whose intrinsic mass has increased over cosmic time. Dark energy, the enigmatic force driving apparent cosmic acceleration, might be a misinterpretation of the very mechanism that causes particles to gain mass. The tantalizing possibility emerges that these two great enigmas, far from being separate components of the universe, are merely manifestations of a single, evolving fundamental constant, the mass of elementary particles. Such a unification would be profoundly elegant, yet its cost is the abandonment of our most cherished assumptions about the constancy of nature. The cosmic microwave background, the universe's oldest light, traditionally interpreted as the stretched afterglow of expansion, would instead become a record of intrinsic energy shifts. Its uniform temperature and characteristic fluctuations would be reread as the relative thermal signature of ancient photons emitted by lighter atoms interacting with our modern, heavier detectors. The universe's memory, etched into this ancient light, would not be of space stretching, but of matter transforming, a silent testament to the evolving energy scales of existence. This challenges not just our interpretation of the CMB, but our very understanding of cosmic temperature and the fundamental constants that define it. The quantum foundations for such a hypothesis are equally speculative and profound. If particle masses are changing, it points to a deeper, more dynamic layer of physics beyond the standard model, perhaps an evolving Higgs field, or subtle interactions with a cosmic scalar field, or even a connection to the elusive theory of quantum gravity. This suggests a universe whose very rules are not static, but are continuously, imperceptibly, being rewritten from within its deepest quantum code. It implies a universe that is alive, not just in its dynamic structures, but in the evolving nature of its most fundamental constituents. Ultimately, the shrinking universe hypothesis stands as a monumental thought experiment, a testament to the boundless ingenuity and terrifying vulnerability of the human mind. It is a scientific proposition that pushes the boundaries of perception, challenging us to distinguish between what is objectively real and what is merely a consistent, all-encompassing illusion. The unfalsifiable nature of this idea, the inability to step outside our own diminishing reality to confirm or deny it, forces us to question the very bedrock of our scientific methodology and our confidence in objective truth. Perhaps the greatest lesson of this chilling alternative cosmology is not a definitive answer, but a profound reframing of our questions. The observable data from within our diminishing frame might always lead us to the same conclusion of expansion. But the existential horror lies in the possibility that this perceived expansion is a grand cosmic deception, a relentless silent erosion of our own scale, leaving us to interpret a universe that appears to grow, when in truth, we are merely becoming smaller. We are cosmic cartographers, mapping a boundless ocean from a boat that is subtly, continuously retracting. Every measurement, every discovery, every understanding becomes a relative truth, calibrated to our current state of contraction. This perspective leaves us with a deep, almost melancholic wonder. If our very being is part of this cosmic illusion, then what other fundamental aspects of reality might be equally distorted by our inescapable, diminishing presence? What does it truly mean to exist in a cosmos where the very ground beneath our feet, the very particles that define us, are in a state of eternal, unnoticeable flux? The universe remains a profound mystery, and our place within it, if this hypothesis holds, is far more precarious, far more existentially unsettling than we ever dared to imagine. We are not just observers, we are participants in a cosmic dance of disappearance, shrinking silently into an unknown future, forever mistaking our own contraction for the boundless expansion of all things.